Okay, welcome back everyone to the afternoon session of this conference. It's a pleasure to introduce Duwenig, who's going to speak today on the Zappa product of a fell bundle and a groupoid. Thank you.
Thank you, Sam. Can people hear me? Is the mic working okay? Wonderful. Okay, so this is on joint work with Boyu Lee. And I want to start with a disclaimer. The results that I'm going to talk about are true for locally compact Hausdorff groupoids as long as they have Haar systems. You don't need to assume etalness. You don't need to have them to have the same unit space. But for simplicity, all the definitions I'll give will be for groups, discrete groups. So you will hear me sometimes switch back and forth between groupoids and groups. The definitions would be really unwieldy if I gave them for groupoids. That's why I do that. So this is what I'm going to do. We're first going to do things only in groupoid land, and I'm really happy that I don't get to give the first talk because lots of people before me have already introduced many things that I need. So I'm going to introduce what the Zappa product is for groups/groupoids, and I'm going to talk about an imprimitivity theorem that Boyu and I proved. And then since we are not only interested in groups, but also in C-star algebras, I'm then going to try to explain to you how Boyu and I came up with a C-star algebraic analog of this group theoretic thing. And if time permits, we are going to see some theorems about them. So let's pretend we don't know anything and start very, very easily with two groups. And I'm going to take their Cartesian product, and I'm going to make another group. You probably have seen this before. So I really just take two tuples and multiply the components. And I get a new group, which is the Cartesian product. Okay, I'm going to take a step back. I still have two groups. But now I also suppose that one of the groups, say H, acts on the left on the space that is G. So forget that G is a group, right? So it's a space and I can act on it. And my little triangle here, this little blue triangle, is pointing at the thing that is being acted on. So I have this new additional data, and I want to make a new group which encodes this action. Okay, so what do? Instead of just multiplying component-wise, I actually pay a price when H1 crosses over G2. H1 acts on G2. Right? And you've all seen this before. You also know this symbol, this R times in LaTeX, right? So I would like this to be a group. But for associativity, I actually need an extra condition, namely, I can't just act on the space, I should actually act on the group, right? I should act by homomorphisms. So I really need that if my H acts on a product, then it's the same as acting on the individuals and then multiplying. Only then is this associative, only then do I get a group. And that's the semi-direct product. Okay, you might have an idea of where this is going now. I'm going to take another step back and assume I have another action, this time on the right. G acts on the right on the space at H. And again, my triangle points at the thing that is being acted on. I do all of this because there's going to be lots and lots and lots of actions floating around. And I hope that the color coding, maybe the blue and the red will help, and the triangle pointing at what is acted on will help. So I have another action. And I would like to, again, turn the Cartesian product into a group that this time encodes both of these actions. So what do? Instead of just paying one price, I pay two prices. So not only does H1 act on G2, but also G2 acts on H1. Again, the question is, when is that actually a group? So when is this multiplication associative? So this time, instead of acting by homomorphisms, I need to act compatibly. So these two actions need to be compatible in the sense that if H acts on a product, then it's the same thing as acting on the first component, and then this changed variant of H acting on the second component. And you need the same for the other action, right? Okay, so if you have this, then you actually also get a group, and that is the Zappa product. And sorry if I'm mispronouncing that name. So I think Karen knows how to pronounce it properly. And so what happens here in the Cartesian product, both groups are normal. In the semi-direct product, only G is normal. In the Zappa product, neither of them have to be normal. So the bottom line, one action by homomorphisms gave me the semi-direct product. Two compatible actions gives me the Zappa product. And if you ever forget which one is acting on which side, up there in the corner is a little reminder. Okay, so these types of two-way actions are really fashionable at the moment. I have been for a while, actually. So for example, Nekrashevich self-similar groups, where you have some finite set and a subgroup of the automorphisms on the finite words. Then there is this condition that if an H acts on a word that starts with the letter X, it's the same thing as acting on the letter and then a variant of H acting on the rest of the word. This is really the same condition as the one that I wrote down earlier. Then there are self-similar actions on directed graphs and K-graphs, Zappa-Zep products of semigroups and of partial multiplications in a very, very, very general settings, or topological groupoids by Mike and other people. So these are really, like, they're around. Like, people are really interested in these types of two-way actions that have some sort of compatibility condition. Now, a little fact, which just maybe gives you more of an idea of how to think about the Zappa-Zep product. If you have some big groupoid K with two subgroupoids G and H, and you assume that every element in K can be uniquely written as a product of an element of G and an element of H, then your K actually is the Zappa-Zep product of these two subgroupoids, sorry. You see me slipping back and forth between the two. And you can find these actions, these two-way actions, by this equality. So take any H and any G, multiply them, right? I land back in K because K contains these two subgroupoids. But by this unique decomposition, I can write it as an element in G and an element in H, right? I can move them past in a certain sense. And then really this element in G that I find, this is really H acting on G. And the element in H that I find is really G acting on H. So you can really compute what the two-way actions are. Okay, so this is the fact just repeated. And an example of this that you might have seen at some point would be the invertible matrices of size n by n is the same as the Zappa-Zep product of the unitaries and the upper triangular matrices with positive diagonal. So just as an example. Another example due to Mike and collaborators, say you have two commuting surjective local homeomorphisms on some topological space. And you assume that they commute in a very, very strong sense. So they're star commuting, meaning that whenever you can write an element as Tx and Sy, then actually this input X and Y already has to come from a Z, namely X is Sz and Y is Tz for a unique Z. So in this situation, we get Diacono-Renaud groupoids of these two local homeomorphisms. So I get one, the natural numbers acting on X via T or via S. And I can also think of n squared acting via T and S. And this really decomposes as a Zappa-Zep product of these two smaller Diacono-Renaud groupoids. And you will see with this example, you really have, it's very symmetric. So these two groupoids that make up the bigger groupoid, they are very, very similar to each other. I wanted to make a comment mainly for people that already know Zappa-Zep products, namely that the construction that we have done is a little more general than what you can find in the previous literature. So in the previous literature, to construct the Zappa-Zep product of two groupoids, you actually need the two unit spaces of the groupoids to be the same. Luckily, unit spaces were introduced earlier, so I hopefully don't have to remind you what they are. And you actually want the moment maps of the actions to be the range and source maps. But we were able to actually allow that one of the unit spaces is larger than the other, surjects onto the other. And then the moment map is allowed to be different than the range map. And luckily, this gives you the choice of having one of the two things be a groupoid and the other thing being a group. So there's a lot more room to do very interesting things. And some of our theorems are most interesting if you pick one of them to be a group and the other to be a groupoid. Just wanted to mention that. And it does become a little bit more complicated, though, because all of a sudden the roles of G and H are less symmetric than I mentioned earlier. So now for some theorems. So recall a theorem that you might know as Green's theorem. There's also a generalization by Kalizewski, Muley, Quigg, and Williams. So we start with two groups H and K. and a groupoid G, and we assume actions on the groupoid on the left and on the right. If the action of K on G is free and proper, then the quotient by that action is actually also a topological groupoid. So freeness you need for the algebra to make sense, and properness you need for the topology to make sense. If that action of K commutes with the action of H, then the quotient actually also has an action of H. And if that action is by homomorphisms, the original action, then so is this new action on the quotient, and we can look at the semi-direct product. So we get a groupoid by what I mentioned earlier. And the cool thing then is, like this theorem is, if you have the exact same properties for the roles of K and H reversed, so again, you need free and proper action, and also you need it by homomorphisms, then you get a second groupoid, the other semi-direct product. And these two groupoids actually are Morita equivalent. So they are equivalent in the sense that if I look at their C-star algebras, I get Morita equivalent C-star algebras. One specific example would be if I take my group K to be trivial, I get that the semi-direct product is Morita equivalent to the quotient by the other group. And here is again the Morita equivalent statement that I just mentioned. Okay, so you've seen me do this before. I take a step back and want to do the exact same thing for the Zappa-Zep product. So this is what Boyu and I did. You start with 3 groupoids. So this is one generalization already, like we didn't need H and K to be groups. They're also groupoids. And this time we have loads of actions. So H and K both act still on G, but G also acts backwards. And I would like to mimic this theorem. Okay, so in the very beginning, I don't really do much. I need still free and proper actions that commute in order to get a quotient groupoid that admits another action. Same thing as before. This time, instead of okay, I forgot about that one. I always forget about that one. So I also need that these actions of G on the other two actually leaves the other two actions invariant. Because if you do that, then the quotient actually acts in the other direction. Now I would like to make a groupoid. So instead of acting by homomorphisms, I need to have a compatible action. So I get this Zappa-Zep product groupoid. And if the situation is symmetric, so all the things that I asked of these actions that I mentioned here are also true for the respective other one, then I again get 2 Morita equivalent groupoids. And one more time, if I take one of the 2 groupoids, H or K, to be trivial, I see that the Zappa-Zep product is Morita equivalent to the quotient, and same, I get this C-star algebraic statement. Oh. Graph product of groups, I don't know. Sorry about that. It's just old green, older theorem. I just don't know this name. Okay, so one more time, this is just what I just mentioned. If you have 2 groupoids that act in a certain way on each other, I get that the Zappa-Zep product of these 2 groupoids is Morita equivalent to the quotient. And so, for example, if I go back to these star commuting local homeomorphisms on some space X, and I get my 2 Diacono-Renault groupoids, then I get an equivalence of the Zappa-Zep product with the quotient. And the quotient is actually, at least for certain nice homeomorphisms, another Diacono-Renault groupoid that I can describe. And here the disclaimer is the certain is a little restrictive. Like we would like it to be a little less restrictive, but I swept a lot of assumptions under the rug with the word certain. So now let's move to C-star land. I repeat what happens in groupoid land. I have a left action of H on G. If it's by homomorphisms, I get the semi-direct product. And my multiplication is defined by paying 1 price. And if you do the computation, you see that this is your formula for inversion. Again, you pay a price when you invert. Right? Okay, we all know how to turn this definition into a C-star algebraic definition. This time I assume my group or groupoid H to act on a C-star algebra A by star homomorphisms, and I get a new C-star algebra, the cross product. And so if everything's discrete, I can think of this guy here as being generated by point masses times elements of A. And I really just copy paste the formula, right? So I take two standard elements of my cross product, A1 at H1, A2 at H2. And when I multiply them, I pay a price of H1 acting on A2. And I land otherwise in the fiber H1, H2. And similarly, I take my involution, I copy paste my inversion formula, and an inverse becomes a star where it makes sense. So we all know how to do that, and that this really is the C-star algebraic analog of the semi-direct product in group land. So now again, I have this other construction in groupoid land, which is the Zappa Zep product, where I have two actions and I pay two prices. And the question then that arises is, if the semi-direct product becomes the cross product, what does the Zappa Zep product become in C-star land? And maybe especially, what is the backwards action of the C-star algebra back on the groupoid? And if I figure out what that is, what results that we know about the cross product can we generalize about this new Zappa Zep product? So that was the question we wanted to answer. Ah, yes, very good point. That will come up. Yes, Excel's C-star blends will come up. Okay, so the question just repeated, what is the analog of G bow tie H? And if you haven't picked up on it yet, by the way, my little bow tie is purple. It's a mix of blue and red. Okay, so our solution to this question was, instead of looking at a C-star algebra, we actually look at a Fell bundle. Because Fell bundles, I will talk about them in detail in a second. They are fibered over, in my case, my groupoid G, and I can then exploit that G acts on H. Okay, so I'll give you the definition of a Fell bundle, but again, the disclaimer, I'm only going to give the definition for discrete groups, because otherwise it's going to get too unwieldy. So a Fell bundle over discrete group G is a family of Banach spaces indexed by the group that come equipped with maps where I can multiply two fibers and land in the fiber over the product. And I can involute a fiber by landing in the inverse fiber. And these actually satisfy loads and loads and loads of extra conditions. So for example, if I take an element in the fiber over G and look at its norm squared, then that better be the same as taking B times B star. So this is now, the B star is in BG inverse. And if I multiply these together, I land in G inverse. So I land in B over the identity fiber, right? And there's many, many other conditions, but this is the flavor of the types of conditions. And again, so if you haven't seen this before, the fiber over the unit is actually C-star algebra, and each of the other fibers is actually an imprimitivity bimodule over that unit fiber. So a Morita equivalence. And again, you can do this for groupoids, it's just more finicky, and then you have to actually be worried about topology. So it's not just a bunch of spaces, but actually they have a global topology that stitches them together. Okay, so if I start with a Fell bundle, I can actually build a C-star algebra out of that. And we do that very similarly to how we have seen earlier how to make a groupoid C-star algebra. So I start with the compactly supported continuous sections of my groupoid into my Fell bundle. So I want, whenever I feed it an element in G, I want to land in the fiber over G. And I give this a convolution product and an involution. And if you remember the talk earlier, this formula looks exactly the same as it does for the Ital groupoid C-star algebra, right? It's exactly the same formula. And same with the involution, just that my complex conjugate is now a star. So here, this here is the multiplication in my Fell bundle. It's not just multiplication of complex numbers, right? My fibers are not just complex numbers, they can be Banach spaces. And then I complete that in some norm and get a C-star algebra. And when I say some norm, there's multiple choices of norms, right? So there is a full C-star algebra, a reduced C-star algebra, things in between. But I'll be mostly interested in the full one, and I don't want to give you the definition of that norm because it's not really important for the the way that my theorems are phrased. Okay, so again, as I remarked earlier, this convolution product uses the Fell bundles multiplication, and that's where all the interesting things are happening, right? So while this formula might look very easy, this multiplication can be very intricate. Lots of things can happen there. And I want to show you that you should actually care about the definition of Fell bundles, because I know that it's a little hard to digest with all this extra structure and all the many properties that I've swept under the rug. But I want to explain to you that a Fell bundle such as this gives rise to many of the C-star algebras that you are used to and want to work with. So let's start with a very simple example. I start with my group being trivial, and the fiber over that one element that I have to be just one fixed C-star algebra. So at this point, what do I need? I now have my bundle of Banach spaces, but I still need a multiplication and an involution. Well, I have a C-star algebra, so I just take the multiplication in the C-star algebra and the involution in the C-star algebra. Nothing interesting happens. And then in this case, the sections of that bundle are really just the C-star algebra. Nothing else, just elements of the C-star algebra. And the C-star algebra that I get from this bundle is the C-star algebra I started with. Okay, group C-star algebras are another example. This time, I'm going to swap which of the two things is trivial. This time, my G is some group, and my fibers are all constant, the complex numbers. So the fibers are always just the exact same Banach space. This time, my multiplication is multiplication in the complex numbers. But note, I switch what fiber I'm over, right? So I multiply something in the G1 fiber with something in the G2 fiber and land in the G1, G2 fiber. But otherwise, it's just regular complex multiplication. Same with the involution, right? The only thing I do is change what fiber I'm over. This time, the sections of that bundle are just the functions defined on my groupoid or group that I start with. And the C-star algebra is the group C-star algebra. And you can do this for groupoids just as well. Now, in the last talk, we've even seen twisted group C-star algebras. And these can also be modeled by Fell bundles. So this time, my data is that I also have a 2 co-cycle, like the one that Elizabeth was talking about as well. And this time, I twist my multiplication a little bit by introducing this co-cycle that depends on which 2 fibers I was living over. And I also twist my involution by this co-cycle. And if you do that, surprise, surprise, you don't get the group C-star algebra, but actually the twisted group C-star algebra. And you can even do this for Kumjian's very general twists. They're also modeled by Fell bundles. And lastly, cross products. Also, this time I fix some group. My fibers are all the exact same C-star algebra A, not just the complex numbers. I assume that my G acts by star homomorphisms. And now my multiplication needs to make sure that this action is being taken care of. So when I multiply A1 with A2, I don't just multiply them in the C-star algebra, but I first pay a price of depending on what fiber of my first component was in. And likewise with the involution formula that I have. So I adjust it a little bit. And in this situation, if I take the C-star algebra of that Fell bundle, I actually get the cross product. Okay. Just to reiterate what I've just done. I had certain input, for example, the C-star algebra, made a Fell bundle, and I get the C-star algebra back. I have a group. I take the Fell bundle that's constant, the complex numbers. I get the group C-star algebra. I take a twisted group. I get the twisted group C-star algebra. I have a dynamical system. I get the cross product. So at the end of the day, Fell bundle C-star algebras are everywhere. You really should care about them. And let this be the absolute minimal thing that you take away from this talk, right? So even if you don't care about anything else that I say, this is important. Please care about Fell bundles. Okay. So now that I've given you the definition of Fell bundles and I started with motivating why I needed it, let me actually tell you how we constructed a C-star analog of the Zappa Szép product. One more time, my question is, if the semi-direct product becomes the cross product, what does the Zappa Szép product become in C-star land? So here in gray, I hope you can see that it's gray, I just repeated exactly what we had earlier. In groupoid land, if I have one action by homomorphisms, I get the semi-direct product where I pay one price. And in C-star land, this becomes the product where I also pay a price in my multiplication. Now in groupoid land, when we had two compatible actions, instead of getting the semi-direct product, we got the Zappa Zep product. And this time, my multiplication paid 2 prices, and the inversion then also pays 2 prices. Okay, so now I want to do the same game in C-star land. And what I do is I start with a fell bundle B over G, this other group, this groupoid group, and I have H act on that in a compatible way, whatever that means. So there is some conditions that it needs to satisfy, this action. And if I have that, I can construct another fell bundle, which is this fancy bow tie symbol, just so that you know that it's not the algebraic one, but the C-star algebraic one. And what I do is that for an element over the Zappa Zep product of G and H, the fiber of that new fell bundle is just supposed to be always BG. So just whatever GH you start with, always it's the same fiber BG of my original fell bundle that I started with over G. Okay, so now I have to give this thing, in order for me to make it a fell bundle over the Zappa Zep product, I need to give this thing a multiplication and involution, right? What I did earlier with the cross product is copy paste the formula of the semi-direct product, right? So here, this is the cross product multiplication and involution, and this came from the semi-direct product definition, right? But what I actually want to model is the Zappa Zep product definition, right? I want to model that. And so what I do, now remember, this is just exactly what I have in the upper line, right? The upper line and this line is now the same. And now I just do the exact same thing. I mimic this formula in my new fell bundle. So what I do is I say, okay, take an element of this new fell bundle that I constructed. An element always looks like something in BG and some H. And I want to multiply this with something in some BG2 and some other H. And I just copy paste this formula. What I do is I multiply in my fell bundle. That's what this dot here is. But I pay a price. My H acts on B2. And then conversely, I also would like to multiply the second components, but again, I pay a price. And this price here that I pay of this B2 on H1, it really is just figuring out in what fiber my B2 lives, right? That's all it does. So it just figures out in what fiber you're in, and depending what fiber you're in, you pay a different price. And then likewise, if I look at my inversion, this now becomes my involution formula. I do the exact same thing wherever inverse that doesn't make sense. Oh, yeah, that should not be an inverse here. There should be a star. So wherever there shouldn't be an inverse, there should be a star. This is the involution in my fell bundle. And just as I mentioned before, this part here, this is where I need that I started with a fell bundle. I started with something that is fibered. I started with something that knows what my group G is. And this is basically the backwards action of my C-star algebra on my groupoid. Okay, here the definition where I get to swipe everything under the rug, which is what does it mean for this H action on my bundle to be compatible? Basically, I just say whatever conditions you had on the original H action on G, mimic that on the fell bundle level. So for example, my compatible action of G and H looked like this, right? If H acted on a product, it's the same as acting on the first component and then a variant acting on the second component. And I want the exact same type of thing to be true in my fell bundle, where if I act on the product in my fell bundle, it's the same as acting on the first and then taking the fell bundle product with a variant acting on the second. And you do that with all the other axioms that you have. And then the theorem that you might have already expected is that if I have this input, then I really do get a fell bundle over the Zappa Zep product. And we called that the Zappa Zep product of the fell bundle with the groupoid. And in our recent paper, we actually started calling it the self-similar product, because we moved away a little bit from the restrictions of Zappa Zep product. Okay, so we now have a candidate of what the C-star analog of a Zappa Zep product is. Here's my theorem repeated. If you have good enough actions of G and H on each other and of H on a fell bundle over G, then you get a new fell bundle over the Zappa Zep product. So this is not only a generalization of the cross product that we all know and love, but it actually also generalizes other theorems that already existed in the literature about more general type of semi-direct products of groups on fell bundles. So if you start with a good enough groupoid action or group action, I think in their case, on a fell bundle, you can construct a semi-direct product fell bundle over the semi-direct product. And ours really is a generalization of that, our construction, if you assume one of the actions to be trivial. Right? Let me give you a small little example just to see that our construction fits nicely with trivial examples. So start with these compatible actions of G and H, and assume that you have some C-star dynamical system of the Zappa-Zep product on some C-star algebra. So really, you just have an action of this groupoid on a C-star algebra. And then you can construct the fell bundle of this C-star dynamical system. And it's actually the exact same thing as taking the fell bundle of the restricted action on G and then taking our fancy Zappa-Zep product with the remainder, with the stuff that you forgot about. And if this doesn't mean anything to you, then maybe the next example will. If you say you have actually no dynamical system, you really just start with the complex numbers, your only input is your Zappa-Zep product groupoid, then this means that if you take the trivial line bundle of the Zappa-Zep product, it's the same as taking the trivial line bundle of one of them and then taking our fancy C-star algebraic Zappa-Zep product with the other. Right? So our construction is not a little stupid. Right? It plays nicely with simple examples. Okay, let me recap what we've done. We started with groupoid constructions. If you have no actions, you have two groupoids, you get the Cartesian product. If you have one action by homomorphisms, you get the semi-direct product. If you have two actions that are compatible in a certain way, then you get the Zappa-Zep product. And then we moved that into C-star land. Again, no actions, you have a C-star algebra and a group, you get the tensor product. One action by star homomorphisms, you get the cross product. You have two actions on a fell bundle that are compatible, you get the Zappa-Zep product. So looking at it like this again, natural question that arises is, what things can we say about the C-star algebra that we can say about that C-star algebra, right? So what sort of properties do they share? Or what sort of statements we can make about the cross product can we also make about this new C-star algebra? Okay, so does it have similar properties or can we prove similar theorems? So one thing, for example, that you might remember when learning first about cross products is that they have a certain representation theory, right? So if you start with a covariant representation, what that means is I have my dynamical system H acting on A, and I assume that I have a representation of my C-star algebra and a unitary representation of my group on the exact same Hilbert space. And then the covariance condition between these two representations is that if I want to move the unitary representation past the C-star algebraic representation, I pay a price of acting on A. Right? And then an old theorem is that the covariant representation of the dynamical system can be integrated to star representations of the cross product. And actually, maybe more interestingly, representations of the cross product can be disintegrated to covariant representations. Right? You've seen me do this a few times. I'm going to take a step back and try to do the exact same thing for my Zappa-Zep product. So I start with a new definition, a covariant representation of one of these nice inputs that I need in order to build this new Zappa-Zep product. I start with a representation of my fell bundle and a unitary representation of my groupoid. And instead of just paying one price when I want to move over, I pay two prices because that's the name of the game. So this time, instead of just having H acting on my B, I also need the fiber that B is living over to act back on H. And then you might know what's going to come next. Our theorem that we proved is if you take covariant representations in that sense, you can integrate them to representations of the C-star algebra of the Zappa-Zep product. And if you have such representations of your Zappa-Zep product, you can disintegrate them into such covariant representations. Okay, wonderful. So I know a little bit about the representation theory. But the question keeps going. Do I have other properties that are similar? And now I come back to what George said, because George asked about C-star blends. So Excel proved that if you have a group acting on a C-star algebra, then actually the cross product or the multiplier algebra of the cross product and the C-star algebra of the groupoid together with the original C-star algebra we start with is a C-star blend. So this is a generalization of a cross product. The cross product really is the leading example for his definition of a C-star blend. And then Mike with collaborators showed that if you have compatible actions of two groupoids on each other so that the Zappa-Zep product makes sense, then actually the Zappa-Zep product C-star algebra is a C-star blend of the two other C-star algebras. And surprise, surprise, we proved a very similar theorem, at least for Fell bundles where the fibers over the C-star algebras over the units are all unital C-star algebras. So here you have again a compatible action on my Fell bundle, and then the Fell bundle C-star algebra of the Zappa-Zep product is a C-star blend of the original Fell bundle C-star algebra and the original groupoid C-star algebra. Okay, now we are going to get to the big imprimitivity theorem. So this is what we had earlier, right? I mentioned earlier that Boyu and I proved that given three groupoids, H, K, and G, if I have these two-way actions in all the different directions, so not only do H and K act on G, but also G acts backwards in a compatible way, I need the actions on G to be free and proper and leaving the other two actions invariant. And then I had this nice statement. Okay, so what was this again? The actions being free tells me that the quotients by these actions are actually groupoids in an algebraic sense. The actions being proper told me that they're actually topological groupoids, actually nice locally compact Hausdorff groupoids. Then what I could also do is that because of this invariance condition, I get compatible actions of the groupoids on the respective other quotient. And because these are compatible in a nice way, I actually get Zappa-Zep products, and they're actually equivalent groupoids giving me equivalent C-star algebras. So Morita equivalent C-star algebras. And now we're going to bootstrap from here and go to Fell bundles. Oh, that was the wrong direction. There we go. So this time I start with two groupoids H and K and a Fell bundle over G. This time my input is that I actually have compatible actions on this Fell bundle. And otherwise I just keep assuming that my actions are free, proper, and leaving the backwards action invariant, exactly the same condition as before. And now not only do I have that the two quotients are groupoids, but actually I can also construct quotient Fell bundles over these groupoids. So I can really make sense of quotienting out by one of these actions and getting another Fell bundle over this quotient groupoid. And then, sure enough, you also get two-way actions that are compatible of the respective other groupoid on that quotient. And lovely, these are actually also, again, equivalent Fell bundles. And I keep forgetting to make the fancy bow tie here. So this should be the fancy C-star algebraic bow tie, right? So this is really the Zappa-Zep product of Fell bundles. And one more time, a corollary that comes from this is that the C-star algebras of these Fell bundle are therefore Morita equivalent. And I should mention this semi-direct product constructions of Fell bundles with groupoids by Kalizewski, Muley, Quick, and Williams is really a specific example of our theorem. Okay, and you can play a nice game as I did before, where you take H or K to be trivial, and you get some nice statement about a Zappa-Zep product being equivalent to a quotient. I actually don't know. I doubt it, but I don't know. I haven't thought about it. So I just mean the existence of an imprimitivity bimodule. So I should probably just say there exists an imprimitivity bimodule between the C-star algebras. It's just a little easier to say Morita. Okay, so these were the theorems I wanted to talk about, and now just for some future things that I'm thinking about. An obvious question is, what properties does my new Fell bundle actually see? And at this point, I really don't know. So I get asked this question a lot, and we don't know yet. So this is something to investigate. what new examples do we actually pick up with our theorem? So aside from, right, we are generalizing theorems about groupoids, and we are generalizing examples of the semi-direct product of Fell bundles, but still, is there anything else? Is there anything in between that we're picking up on? One problem that we have is that our theorems are really only interesting if you look at groupoids because of this freeness condition. Because as soon as you have a group, you can't act freely in the right sense. And so you really need groupoids, but the problem is there is not that many Zappa product of groupoids around yet. So there's just not many examples that we can play with. So these star commuting endomorphisms that I mentioned twice that Mike came up with his collaborators, this is one of the few examples that we've had. And then a question that I've been wondering about with Shanshan, for example, and some others is, can we play this game with other input? So say we start with a self-similar K-graph a la Yang and Lee. Can we construct a Zappa product K-graph, or maybe K+1 graph, or K+n graph, or something like that out of this? And I fear the answer is no. I think you leave the realm of K-graphs and just remain in the realm of categories, but we don't know. Maybe we have not been looking at it the right way. And that's all I wanted to talk about. Thanks.